But the title of my talk today is Signposts for Latency and Reliability on the Way Beyond 5G Wireless. And the reason for this is that I've been asked by one of the industries to give a talk tomorrow about what ultra reliable low latency will look after 5G, and what did we do maybe wrong in 5G. And I said, okay, that's a good opportunity to reflect a little bit, and maybe not going to just take one topic and discuss about it concretely, but put a little bit of broader perspective on the topic. I hope that will be useful for you as well. This is the outline. So we're dealing with several signposts. So first, I'm going to briefly go through connectivity types and traffic modeling. There are parts which you're very familiar with, but there are some which I believe are new. Then we go to the target performance parameters. I'll spend more time on this part. Then machine learning, which is the central theme of your project. And I will speak about what is a must-have and what is nice to have with respect to latency and reliability. Then spectrum and slicing, and basically how it should coexist with other types of services. And finally, one topic which seems a bit off, but I will try to argue why it is important to consider it for the upcoming generation of latency-constrained wireless communications. So let's start with connectivity types and traffic modeling. So this is the 5G mantra that we all know about. And it is the three services: enhanced mobile broadband, massive machine type communication, and ultra reliable low latency. Then the way we should understand this is that these are the three services from which we are going to make all types of connectivity that we are going to need in the future. At least that was the ambition. And the interesting point about 5G is that roughly 2/3 of 5G is dedicated to IoT communication, and the ambition is to connect the vertical sectors, the vertical industries. So, so there have been, discussions about 5G. What is the most innovative thing? Is the ultra reliable low latency? But that is still being standardized. There has been no new waveform. That was maybe not the most innovative part. In my opinion, the most innovative thing about 5G is the platform approach, because 5G has this approach that is going to make a connectivity platform, and then that platform will be used as a substance to create any type of links and connections within with different needs, right? And then somehow we judged already at the beginning at actually in the Metis project together with Hugo and some other colleagues, we kind of thought that there will be these three types of services, and that turned out to be true. One is broadband, which is can be understood as acceleration of 4G, large payloads, activity over long periods. We want to maximize the rate, but we need some moderate reliability. Then is massive machine type communication, where we have fixed low rate. We have a large potential subset of transmitters or devices we want to communicate with. We want to maximize the arrival rate, the activation rate from these devices. The reliability per device may be low, but overall the reliability from a population of devices should be high. And ultra reliable low latency is, as I said, the new type of service which was included in 5G, because EMBB and MMTC, they existed before. MMTC was all these wide area IoT networks, and then NB-IoT is an instance of it. But ultra reliable low latency is really native to the 5G concept and the 5G standardization. And to my knowledge, Wi-Fi is also going in that direction to propose this type of connectivity. So the idea in URLLC is to have intermittent transmissions from much smaller device set compared to MMTC, offer very high reliability, for example, 10 to the -5, while localizing time. So we are going to discuss a bit what is this 10 to the -5 later on in the talk. And so the way the platform works is that we have these three types of connectivity services, and then any type of connectivity can be made by combining them. Right, so we have a certain connectivity need in industrial automation. So industrial automation, we need sometimes ultra reliable low latency, sometimes massive machine type communication, and sometimes EMBB. But the question is this the ultimate connectivity framework? Actually, this is not mathematically proven, because we just thought, we and other colleagues around the world, we just thought that these three types of connectivity would be sufficient to create any type of connection. And then we hypothesize that this defining these three types of connectivity will be sufficient. The problem is that I will quote here von Neumann, who said that it will appear that we have reached the limits of what is possible to achieve with computer technology, although one should be careful with such statements, as they tend to sound pretty silly in 5 years. Meaning that if somebody says, well, 5G is defining everything, why do we need anything beyond 5G? That might turn out to be silly, in a couple of years, because of the exponential pace by which this technology is developing. And in case you are in doubt who are the other two people on this picture, is actually Richard Feynman and Stanislav Ulam. Stanislav Ulam is the guy who started with Monte Carlo methods. So how is this related to other wireless interfaces? Because there could be a question: if 5G dominates and beyond that 6G starts to continue this dominance, what is there left for the other interfaces? So I think the open-minded way to look at this is that we have certain population of connections. There are these different shapes here, which I've made. And then there are these connectivity types like EMBB, NTC, URLLC. And we are going to use these connectivity types as, as three vectors in some connectivity space to support any of these type of connections. But of course, things are getting complex, because if there are multiple connections that want to simultaneously coexist, how are you going to compose them? How are you going to allocate resources to them? This is the issue which is addressed through the approach of slicing in 5G. But saying just slicing is not enough. I mean, the way you are going to allocate the resources and you are going to orchestrate all these resources requires complex algorithms and definitely machine learning. And then once we have these connectivity types, we can actually map them to different wireless interfaces. And I don't believe that Wi-Fi will disappear, because my hypothesis is that at least 90% of us at this call are using Wi-Fi at the moment, right? So it's difficult to think that this local area network will just disappear if 5G comes. Then another point which is important is that the ultra reliable low latency embeds two concepts: very high reliability and low latency. And for a long time, the requirement that was around was that we require error rate of 10 to the minus 5 under this proverbial 1 millisecond. The thing is that if we give what information theory says, that there can be a perfect reliability, of course, under two conditions: if we allow infinite latency, and if we know exactly what is the channel statistics of the channel in question. I mean, this is the if we know that what is the capacity of the channel and we transmit below the capacity and we give infinite time, then the reliability will be perfect. Of course, we don't have that in reality. And if Hugo and my other colleagues from Metis remember, this was not always the case, that ultra reliable was coupled with low latency. We discussed actually at the beginning that we could define two types of ultra reliable communication: more than 10 milliseconds, that would be a long term; less than 10 milliseconds, that could be a short term. This was based on discussion with a lot of stakeholders in the project. So we still need latency constraint for high reliability, because otherwise, we are not going to satisfy these real-time applications. But the value of 1 millisecond needs to be revisited. And there are at least three cases for longer-term ultra-reliable communication. One is the mobile health, remote monitoring, where a millisecond is not critical, but seconds could be important. Then we have disaster and rescue, where milliseconds and seconds are not important, but maybe minutes are important. And then we have smart grid, where there are a lot of use cases where basically we have to be synchronized to 20 milliseconds, which is the cycle time in a 50 hertz network, right? So and this is not stopping here. And even there is I really recommend that you go to check the documents of 5G. ICIA is this 5G group for industrial automation. They have very high quality white papers. And this is from one of their latest white papers, which is defining different notions of real time. There is non-real time, soft real time around the second, and hard real time milliseconds and even microseconds. And actually, they define different types of use cases and map them into hard real time, soft real time, and non-real time. The important takeaway from this is that we probably need to decouple latency and reliability and have at least 4 dimensions when defining these generic connectivity types. So I've tried to do that, and here are some mappings of possible applications. For example, we have tactile robotics, which requires high reliability, low latency, not very high data rate, and not very massive. So this is kind of URLLC. But if we have health monitors, we need high reliability, latency can be relaxed, data rate can be relaxed, but we need a massive number of devices. Then augmented reality, we have high data rate, low latency, relatively, reliability and massiveness can be relaxed. The question is, what are the trade-offs within this space? I mean, if you decrease the reliability, how much can you gain in data rate? What is possible with certain budget? Actually, these are fundamental questions which are difficult to answer simply because it's difficult to make a relatively simple theoretical model to analyze this. And actually, our colleagues from Ericsson thought in a similar direction, and they also thought that having only massive and ultra reliable is not enough. So there are 4 different types of IoT that they have defined in an interesting white paper from last year, which is massive IoT, broadband IoT, critical IoT, industrial automation IoT, which I have tried to map to the 4 dimensions I have defined. We have the massive, we have the broadband, we have the critical, and we have industrial automation. Then, and this is the main takeaway from this part, we need to have improved understanding of the connection ecosystem. So if we take the population of the connections, we are mapping them to 4 generic connectivity types, one offering reliability, one offering latency, one offering data rate, and one offering massiveness. But I think the complexity arises when we start to look into composite connections. For example, we have low latency traffic arrivals from the same device combined with broadband requests. And as you see here, there counts a very high reliability request. So the question is, can we make traffic models where we have temporal and causal dependency between different traffic types? And this is a research question to address in the coming period. Then let's look into the target performance parameters. So if we start with a very simple model of a single link, this is what we have usually in mind when we speak about what is the data rate that we can transmit, which operations we need, and so on. So if we have this link, then we have the Y is the received signal, X is the transmitted data, alpha is the user activity, H is the channel state, Z is the noise, and W is the interference. Then we can say that the objective of our system is to find alpha, whether the user is active, and if alpha is active, find what the user is transmitting, which is X. So latency reliability characterization. This curve is very handy to describe latency and reliability in wireless in communication systems, where on the horizontal axis we have the latency, and on the vertical axis we have the probability that the packet will arrive until a certain time. And this can be plotted if we have a fixed data size and we have a certain communication system, we can always plot this curve. You can find it empirically, calculated through experiments and so on. And this curve is normally thought in terms of one-way latency, but we can also think about two-way latency, for example, transmission and acknowledgement, and then we can include this into this characteristics. And we can improve the latency reliability characteristic by introducing diversity. Diversity can be in time. For example, we can have certain type of coding, although that's very limited because we don't have sufficient time to do diversity. Actually, on the next slide, I will show you that some interesting consequences what we can do in time. And we can use frequency diversity. We can use many antennas. We can even use multi-connectivity in different interfaces. And these are all options to introduce diversity and improve the reliability of the system. So in a broadband rate-oriented system, what we want to do is we want to decrease the average time by which the packet is transmitted, which means that we are increasing the average rate. But in ultra-reliable low-latency communication, we want to meet the certain reliability target by given time. And we want to move from the blue curve to the red curve, where the red curve is meeting the deadline with certain probability, with certain reliability. The interesting point I mentioned before with the diversity in time is that the green curve is also meeting this. The green curve is telling us that we might actually optimize the system, not for throughput, but we might optimize it for specific transmission at the time intervals at which the packet should arrive. So that's quite different from optimizing the system on average, right? So you can actually formulate this as an optimization problem, and it might turn out that the optimal latency reliability curve for a certain system is like the green one, not like the red one. So what are the trade-offs in a single transmission? So let's get this thing straight with what is the relation between time, bandwidth, and so on. So let's fix the latency to t. Let's fix the data size to d, which is number of bits. So that means that the minimal required data rate of the system is d divided by t in terms of bit per second. So the system cannot have data rate which is less than this. Then let us fix the bandwidth to b. And let's assume that the system is not frequency selective, just for the sake of clarity at this point. This gives 2 BT channel uses, right? So we have a bandwidth, we have in total 2 times BT channel uses, or 2 times BT symbols that we can send in a system which is a Nyquist sample. Then the rate per channel use is D divided by 2 times BT, which is R divided by 2B, where R is the data rate, and B is the actually this is wrong here. It should be the rate in terms of bits per channel unit, and this R is the other, is RBPS. Anyway, the point is that the number of bits per channel unit is decreasing with the bandwidth, meaning that if you have more bandwidth, you can have you put a lower rate requirement on your transmission. Then fix the energy spent in T. You know, this energies could be the transmission energy, you fix your receiver, you fix all the energy you're spending on your reception and so on. After you fix all these things, then the maximum reliability is implied by the selection of the previous parameters in the subject of fundamental limits of information transmission in noise. So that means that if we have the SNR in that previous channel model, and we fix the latency, we fix the bandwidth and so on, we can see what is the error probability. And actually you can interchange this. You can say, if I fix the maximum reliability and latency, what is the bandwidth I should use to achieve that, right? So that is kind of the question that you want to ask if the latency and reliability constraints are given to you. So you can play with all these parameters. The 5 parameters are interchangeable. So it's bandwidth, rate, reliability, energy, and latency, where energy is understood in a very general way. But I think we should look a little bit broader, more generalized to the issue of latency, because I had a discussion with somebody who is running a startup company on augmented reality, and they said, you know, we need to have a 1 millisecond latency of the wireless link because it's very risky and we cannot trust it. But we can have 25, 30 milliseconds, and the image compression module or the video playout module, because we trust it and it's a software which we can control locally. This is, you know, this is a really eye opener, because it says that the latency of the wireless link does not need to be actually very low as long as we guarantee its statistics. So that has been this is another argument to maybe revise this 1 millisecond and focus on offering truly high reliability within several milliseconds. So this big figure is taken from the 3GPP technical specification, where what you can see is we can define the end-to-end latency, for example, in this figure here, or we can have the transfer time of certain vertical applications, which is defined with respect to the arrival time of the vertical application. We have time between the arrival of updates, but there is another interesting measure that we can define, and my group is now working on it. It's called peak age. So you see, the peak age is the time since so this update has been generated here. I don't know whether you can see the cursor, and then it's being received, but that is already old as the transmission time. And then the next update comes after the update time. So the total the total time that is required is called peak age. That's how old is the update when the new update arrives at the receiver. And this is important because the peak age could be a cause of instability in controlled systems and so on. So my opinion is that latency age, peak age are only instances of a class of time-related criteria for mission fulfillment of the system. And for example, another popular criteria that has been used in the industry is consecutive errors. So if there is one time not satisfied over, for example, 10 milliseconds or 20 milliseconds, then they say, okay, let's try one more, let's try two times more, and then after 3 errors, the system goes into a safe state. So this is the basically watchdog criterion for reliability of a link. And the thing which is very important here is that we have a trade-off between a good architecture, which is layering, and flexible timing requirements. And in my opinion, the proverbial 1 millisecond is a victim of layering, meaning that we want to have layered system where we have a communication system that we want to behave in a certain way and deliver certain predictable latency. But because we do not really believe that that layer is going to fulfill it, that's why we put very low requirement on the latency. This is what I heard from people using applications. So maybe we need to reconsider the requirements put on the the latency of the wireless system by allowing an increased level of cross-layer coordination. A more elaborate model is let's take an uplink model, which is I take uplink because uplink is generally harder than downlink due to the lack of coordination between the transmitters. So now the previous model of a single link expands to something, which is here we have the activity of the kth user connected to the system that we observe. Y is the received signal. HK is the channel of the kth user. XK is the data of the kth user. WS is the Z stays the noise. WS is the interference of the same type of a known system. For example, it's another 5G system. WU is interference from other uncoordinated system. For example, this appears in unlicensed spectrum. And WJ is interference from malicious jammer. The interesting thing is that the right side of this equation is full of random variables, but we are only interested in XKs. The question is, what can we guarantee about XK about all these random variables? And actually, even a better question is, are all these random variables truly random, or they're just unpredictable? Because randomness and unpredictability is not the same thing. For example, we'll come to that point. Alpha K can be solved by certain MAC protocols, scheduling or random access. HK is subject to estimation, the channel estimation. Z is true uncertainty, is the noise that we can never know, so it's combated by coding. WS can be combated by coordination because remember, it's the same type of system, so we can in some way coordinate, use some machine learning, some anticipatory techniques to kind of allocate resources and combat WS. W is a spectrum licensing issue. So if we have a licensed spectrum, W doesn't exist. And that's why a lot of the things in 5G go into the direction of private networks. But WJ is jammer, and it's actually very difficult to characterize it in a statistical sense. So in that sense, the question is, what does a reliability of 99.99% mean? Can we guarantee 99.99% of the time that the jammer will not intentionally do something? This is difficult to characterize. So that's why I'm not saying it's impossible to guarantee high reliability, but I think we need to put a bound on what can we guarantee and what we cannot consider statistically as a part of the model. Then, having said that, let's look at the machine learning, which is the central topic of your project. And let's look at about this ultra reliability and latency. What is a must-have from machine learning and what is nice to have? By the way, nice to have doesn't mean that is something which is secondary. Actually, it could be very important to deliver the performance. But I want also to tell what is theoretically impossible to achieve if you don't have machine learning. So let's look at this data-driven performance guarantees where Alice is selling the ultra reliability to Bob. And the question is, how does she measure the reliability performance? And under what conditions is this ultra reliability guaranteed? Does she guarantee it with respect to the jammer, with respect to another similar system? If you go back to my more elaborate model, with respect to which random variables of this model is the ultra reliability guarantee? This is really difficult to answer. And Bob is asking inconvenient question like, what is the true distribution used to calculate reliability? Because if you calculate reliability, you have to have a distribution. The question is, what is that distribution? What if the true channel distribution differs from what you claim to be the distribution? And what if we don't have any knowledge of the distribution at all? So let's assume that the interference is absent. Let's simplify that, it's a little bit scary model with all the interferers. And even let's assume that we somehow know that the channel is Rayleigh. The target error rate is epsilon u, and the average SNR is gamma S bar. How do we choose the rate? Well, you go to a textbook and you say, this is the Shannon formula, although I don't like that expression. And you take this probability of logarithm 2, 1 plus gamma S less than R. And if the probability of error is very low, then we have ultra reliable system. And to find that, you find the rate just by inverting this formula, and you see that you select the rate according to the second formula. The trouble is that this gamma S average is not known, and it's a subject to estimation. So the whole discussion whether we need a model-based approach or data-driven approach, the answer is that we need actually both. We need certain model-based parameterized approach, and then we need to estimate the parameters based on the real data. So the uncertainty in ultra-reliable wireless link, even in the simple link, comes from inherent randomness of the wireless, then the ignorance about the channel statistics. So inherent randomness is that, let's say that you know that the channel is Rayleigh, you have reliably estimated the average value of the SNR, but still you have fluctuations in the channel. So that's the inherent randomness. Then you have the ignorance about channel statistics, which means that it might happen that you do not estimate the channel well, if you don't have sufficient number of samples. And then even if you estimate it well, the channel might change. So there's a concept drift. So all this is bringing uncertainty to the wireless link. So that's why I'm saying that machine learning is a must-have for ultra reliability, because there are three key elements. First is the model selection. We want to make a parametric model for F, the distribution with respect to which we are calculating the reliability. Or if we don't have it, we have to do it non-parametrically. Then, but again, think of the model with a jammer, which I had before. Jammer cannot be part of the training because the jammer is not making itself available to have you to train the model, and then when attacked that you're prepared for it. The point of the jammer is to be surprising, right? Then we have a learning phase where we have estimate of F using the certain training sample. And then the important point here is that the bad training data leads to a bad estimate of F, as in every machine learning problem. And then finally, we have performance evaluation, where each of you that have gone through the basis of statistical machine learning would say, well, specifying just the packet error rate is not sufficient. So let's see why. So let's take a simple case where we can show how the performance evaluation can be done in the right statistical way. So let's take the rate selection as a simplest case. And of course, we have to have more complex examples in reality, like choice of resources in slicing and admission of users and so on, allocation of spectrum. So we define two types of reliability: probably correct reliability and average reliability. So probably correct reliability is inspired by probably approximately correct learning, PAC learning paradigm. So that is telling that it's calculated as a reliability that can be obtained from a specific training sample x to the n. So basically what I'm doing is I'm having a training sample x to the n. Based on this training sample, I'm calculating which rates to choose. And then the packet error probability which I'm going to get for that rate, the probability that the packet error rate is going to be larger than what the ultra reliability wants is less than something. The thing is that here I want to account for the case where the training was bad. So if the training was too optimistic, then I might select very high rate, but then when I transmit, this rate is leading to a lot of errors. This is suitable for static environments, for example, where training precedes operation. This could be in an industrial environment where 10 milliseconds in every 5 minutes are used to train, to select the rate and guarantee certain reliability. Average reliability is calculated as a reliability that is averaged across all possible training samples. So basically, we are sampling the distribution x to the n. We are sampling all possible training samples, and we want to guarantee that the rate selected based on that, the average rate, error rate, will be less than epsilon. And this is, of course, here we do not have the second parameter because we're looking at the whole ensemble of how it's called, of sample production. Then this is suitable for dynamic environments where separate training is not feasible. And if we need if we have parametric estimation, then we need to have a good guess about the channel model. And here's some work where we have actually done this, characterize the channels in ultra-reliable regime. But non-parametric estimation is the most difficult, as usual, because we have to learn everything. We don't make any assumption about the model. So if you want the error probability of 10 to the minus 9, you need to have 10 to the 9 at least samples of a channel distribution, which, by the way, should not change when you use the channel afterwards. It's really difficult. So how does performance evaluation look like? So what we have tried to do here is to show the rate that we are achieving when we are selecting the rate in a careful way, not very aggressively, so that we choose a lower rate and in order to meet the reliability target. But as we learn the channel, we increase the rate because we become more certain what should be the rate. So this is like, you're coming to a new city, you don't know the city well, so you're moving within small area very carefully and so on. But after some time, you learn the city well, you can move with a, let's say, normal speed at the normal any time of the day and so on. So this is similar to it. So basically here we pay a penalty for not knowing the channel, and the black marked is the average reliability, the white marked is the probably correct reliability. And the probably correct reliability, of course, more conservative, because the probably correct reliability is based on single training samples, and the chances that we are unlucky with that is much higher. So what is nice to have for machine learning? Just one slide about this. Well, solving the complex algorithmic challenges using deep learning, and a lot of you in this project are doing this. Resource allocation, cross-layer optimization. You find a difficult algorithmic problem, you have data for it, and then you go ahead with certain deep learning technique or federated learning and so on. Multi-obtain optimization, anticipatory networking. There is actually a recent tutorial of how you could use deep learning in ultra-reliable and low-latency communication, which I recommend that you have a look. It's by a group in Australia. Then let's look into the spectrum slicing. Hugo, how much more time I have? Do I have 10 minutes?
Absolutely. I mean, it's scheduled until 2 p.m. and then we have a discussion until 3. So take your time.
Okay, but I mean, more than 45 minutes, one becomes boring. So let me see if I can wrap up in 10 minutes. So as I said before, the main innovation in 5G, in my opinion, is that it offers a platform for heterogeneous services. And it actually leads to new spectrum usage models like private networks and local licensing. The interesting thing is that if you look into the recent call for project from the EU Commission, which I think, fortunately and unfortunately, some results were available yesterday. This is called Smart Connectivity Beyond 5G. The first sentence there was provision of seemingly infinite network capacity, including innovative spectrum use and management. But the question one can ask when reading this is, how do we measure spectrum capacity? For example, when one user wants a high rate and another doesn't want a high rate, wants a fixed rate, but wants high rate latency and reliability. How do we measure how efficiently is certain chunk of spectrum used? And let me put two examples on wireless slicing to explain why this is the case. Why this is problematic for how we measure the spectrum usage. So we have broadband connectivity, continuous transmission, like for example, video stream, and we have a target target rate as a target. The rate is a target of this transmission. And here we have low latency connectivity, intermittent transmission, certain activation from time to time, unpredictable. Example is reliable control, and there's a target latency and reliability. The thing is that how certain portion of spectrum is used by these two users. Actually, if you allocate it exclusively to the intermittent user, then the problem is that the intermittent user might simply not use the spectrum properly because it's intermittently active. The spectrum will stay idle most of the time. Think of the military spectrum, which is unused most of the time and gave rise to a lot of discussions about secondary spectrum use. Then, on the other hand, the broadband, if it uses a large spectrum, then it's not going to allow a sufficiently large spectrum for the intermittent user whenever it needs it to get highly reliable transmission and high diversity, for example. So I tried to capture this in a very simple example. Let's look at what is called orthogonal slicing. For example, we have a frame. This is a simple TDMA system where we have every Lth slot is allocated to the intermittent user, and the intermittent user waits for at most L slots to deliver the packet, right? So every intermittent user is transmitting. So you can see here that, for example, Y1 is transmitted, Y2 is transmitted when the slot comes, so it waits a little bit, and Y3 is actually dropped because there was no slot until the Y3 expired. And the broadband output is L minus L1 divided by L multiple R. But the important point is that the intermittency of the intermittent user does not affect the broadband output. On the other hand, if we have non-orthogonal slicing, so here is just an example how this could be done. Let's say that the broadband user can have some error. So what we do with the broadband user is we tell the broadband user decrease your rate 3 times and repeat every packet 3 times. Then to the intermittent user, we say whenever your packet comes, just transmit it. What happens is that if you look at this case here, at the first transmission, when there is a collision in slot 3, actually the base station, which I call basil in this case, is having the packet from before. So you can just subtract it and decode the packet Y1. So there can be some successive interference cancellation by which these two can coexist. So I'm not saying that it's better than the previous one in all cases, but it can attain some operating points which are not possible for the other one. So this means that if we want to go for ultra reliable connectivity, we cannot look it into isolation from the other connectivity types. We have to look into the spectrum regulation, allocation of the spectrum, and how the spectrum is used. So spectrum regulation is a very slow process. It takes years to allocate a spectrum. And then once it's allocated, the spectrum regulation is like an axiom in mathematics. You cannot change it. You have to adapt to that axiom. And then we have wireless system design, which is adapting to that, meaning that putting filters, behaving in unlicensed spectrum, and so on. But then now is the time with the heterogeneity of 5G where we have actually new models. And this new model is the new types of trade-off that you can see from heterogeneous transmissions. And hopefully in some years, this is going to affect how the spectrum is going to be allocated. Because maybe the current type of spectrum allocation and the current way of promising infinite capacity, as the EU Commission says, is not the right one. Then the final part, I'll go quickly through it, is to mention what is going to happen to the IoT traffic and to the latency measures by having trusted interactions. So you have probably heard about distributed ledgers and blockchains. So these are systems in which we would like to approximate a truthful, immutable account for the history of transactions. So we would like to have a system where any transaction between the parties can be written in a distributed database, and everybody agrees on the content of this database. And this is, the topic of computer science, how you define these consensuses and so on. The point is that this consensus can be used to have a certain smart contract. For example, the smart contract is saying whenever some industrial machine does something, then you're going to send a certain video stream to something else. This is a smart contract. And the objective here is to have finalized transactions. So finalized transaction at certain high layer. But notice here, and that's a big change, that before we were talking about the latency over a single link, so we're putting 1 millisecond. But the question is, what is the latency at the consensus level? What is the latency of the whole network that is having the distributed ledger is writing something in the ledger and that's verified? Actually, that cannot be 1 millisecond. That should be much larger. And I think the whole area of IoT has a potential to be changed if we introduce smart contracts, because then the IoT traffic is not anymore just a sensor which is transmitting, locally. It has to be part of a global consensus, or at least part of certain localized consensus within some distributed ledger, within some trusted group. Why should we, as wireless community, care? Well, this reminds me of the California gold rush in the 19th century, where people were going to find gold in California, but the people that really earned money were the ones making shovels, right? Because find gold or not gold, you need to use some tools. So in that same sense, we are standing with communication, meaning that whatever the application of the blockchain will be, or the distributed ledgers, or whether it will be called blockchain or smart contract, doesn't matter. There will be a need for a lot of communication. And people have religious views on the blockchain, like I don't believe in blockchain, or I believe in blockchain, and so on. This is not the place to discuss this, whether we should believe in it religiously or argumentatively or whatever. The point is that this method of distributed verification of data is going to take place one way or another, whether it will be with blockchain, with some other types of distributed ledgers. And whatever it happens, the communication patterns will change compared to the case where we didn't account for this. And that's the view of a communication engineer. So that means that the IoT without blockchain look like the one on the left, but the IoT with blockchain will look like the one on the right. So how do we fit distributed ledgers to MMTC and URLLC, especially URLLC, which we mentioned before? So the capabilities and requirements of MMTC and URLLC are quite different. The challenge in MMTC is that the devices are very simple and then cannot really handle the computational requirements maybe for a distributed ledger. The challenge in URLLC is more fundamental, is the transaction finalization delay. So the challenge is, how can you guarantee with certain bounded latency that the transaction is okay, and then that transaction will be accepted? So actually, this is going to lead to a new definitions and requirements on latency, because it's not the latency of a single link, but it's the latency of a consensus. And I think this is interesting for us as a research community. So the distributed trust architecture, briefly illustrated on this figure, is telling you that if you have a legacy system architecture with IoT, then there are peripheral devices connected to some trusted base stations, and these base stations are sending data to the servers. But if you have distributed trust architecture, then you need to have a more capable edge network, which is going to help these devices to be part of the consensus. So this is some results. These are some results that we have measured with LoRa. LoRa is not 5G. LoRa is not low latency technology, but still it's IoT technology. And so we wanted to have a look. What is the latency that we get for acknowledging some transaction? And actually, the latency is horrible compared to what we require in ultra reliable low latency. So here, this is, for example, Bitcoin, which we didn't expect to perform well, was quite good, but Hyperledger Fabric, which is a private permission blockchain, which is more centralized, actually performed very bad. Because what is this telling us is that if you want to have latency optimization for trusted systems, then you need to optimize the segmentation of the packets that are used in the consensus. You cannot use a layered architecture blindly. You remember I mentioned this 1 millisecond was a victim of layering. And if we put 1 millisecond here, with 5G, all these values will go down for this consensus. But to guarantee something about the consensus, we have to use at the plurality. We have to look at the plurality of links, not a single link. So that brings me to the end of my presentation. So what I wanted to say mostly is that there will be new types of connections and new generic types which are composite, and they will require interaction among certain generic traffic types, which I believe there are 4, not 3 only, like in 5G. So there is a latency, reliability, data rate, and massiveness. And we need a better understanding of the models that will bring us to generalization of the notions of timing and reliability. So I'm not saying latency here, I'm just saying timing as a general notion. So as we saw in the last part, the IoT traffic may be significantly changed by smart contracts and distributed ledgers and leads to, for example, collective notions of latency, consensus latency. And machine learning is a must-have for guaranteeing and measuring ultra reliability, but is a nice to have for any optimization of the 5G and beyond 5G network. And I think also spectrum allocation and usage will be revised from spectrum efficiency only to conform to the requirements of different generic types. And that concludes my talk. Thanks.